Welcome to the second part of the Mathematics for Automated Flight Week 5, where we had discussed the second order system in terms of the mass spring and damping coefficients. And we introduced the natural frequency and the damping ratio, which is the damping, actual damping divided over the damping in the critically damped situation, and characterized its behavior. So it's overdamped, critically damped, undamped and underdamped in terms of the damping ratio. Now the natural frequency is the frequency at which the system oscillates if there is no damping. So there's no friction or damping. The system will just oscillate indefinitely, and it will do at the frequency of square root of k over m radians per second. Now I would like to rewrite this equation now as, so I've taken the original equation and divided by m, and we can rewrite this as x double prime plus 2 zeta omega n times x prime. So b over m is equal to 2 zeta times omega n plus omega n squared times x, and that is equal to f over m. And now what I would like to do is take the Laplace transform. And the Laplace transform of that, and just to show you, well, that omega n squared is k over m is evident from here. If I take zeta times if I take 2 zeta times omega n, then I get the square root of k over the square root of m times b times 2 times the square root of m times the square root of k times 2. So this 2 cancels out here, square root of k cancels out there, and the square root of m times itself is equal to m, so this is equal to b over m. So I can really write it like that, but I'm more interested in the transfer function. So the transfer function is the fraction of the output over the input in the Laplace domain, in the S domain, and we are left with this transfer function. Now, for different values of zeta, we get different roots of our auxiliary equation. And what I want to show you is that the roots of the auxiliary equation are the same roots of this polynomial and are the roots of the denominator of the transfer function gs, and those are called the poles of g of s. Transfer function can also have roots. Those are the zeros, and the zeros are the roots of the denominator, and in this case we have none, and they they determine the response of a system when there is an input, and the poles determine the behavior of the system if it is if there's no input, what it does on its own. And we will see if we take the roots, or in this case are basically s1 and 2 minus this term minus 2 zeta omega n plus or minus the square root of this term squared, 4 zeta squared omega n squared minus 4 omega n squared divided over by 2. And if we separate out this 4 and omega n squared, and we also divide by 2, this clears up to z omega n plus or minus omega n times the square root of zeta minus 1. Now, in the case that there are oscillations, we know that zeta is somewhere between 0 and 1. And if zeta is between 0 and 1, this will become negative. And we have poles of the form z omega n plus or minus j omega n times the square root of 1 minus zeta squared. Now I flip these round so that this now is a positive number, and the minus 1 is turned, the square root of the minus 1 is turned into this j. And again, what we see is that if we have our, if zeta is larger than 1, then this will be positive, and we have two distinct real roots. So we have this case again. If zeta is equal to 1, this root becomes equal to 0, and we only have one root. Again, the same root here. If zeta is equal to 0, then this term drops out, and we are only left with S1, S2 is equal to plus or minus j omega n, and that is the case where we have no damping, where it's purely where it oscillates in its natural frequency, and that's the undamped solution. And then we have this case where we do have oscillations, but we have the real part, which we'd call alpha, and the imaginary part, which we had here we have j beta, beta, and we are in the realm where we have an underdamped system. But one of the interesting things here is that if we're here, if zeta isn't equal to 0, we have some damping. And what we see is that it is damped. This alpha is equal to, minus zeta omega n, and both are positive numbers. So alpha will be negative, so we do get this dampening out of our oscillations, but the frequency is equal to beta. The frequency here, if we have damping, is equal to omega n times 1 minus the square root of zeta. And this is called the dampened frequency. And you see they're not quite equal. If there is practically no damping, you'll see this goes to the natural frequency, and if there's a lot of damping, slowly but surely, yes, then this will go to 0, so the damped frequency will become smaller and smaller and smaller. So the frequency is smaller, so the oscillations become longer. So, so in the first video, we characterized the behavior in terms of the damping ratio and the natural frequency. We now can see that if we take our differential equation and rewrite it slightly, take the transfer function, that the poles of our denominators, the zeros of the denominator, so our poles of our transfer function are the same poles, the same classification as we get in the first part of the video, so are different forms of damping, and that we have a frequency of the system that is not equal to the natural frequency in the case of damping, which is given by this formula. All right.